A crab might seem like it leads a strange life at the bottom of an aquarium or an ocean. Underneath all of that fluid, immersed in this water, having to move through it as it scuttles about. Pretty strange indeed, unless you consider that from a certain point of view, we are all of us crabs. You're a crab too, living in an aquarium, scuttling around on the bottom of this aquarium. It's just that your aquarium is filled with a gas instead of a liquid, a fluid nonetheless. The Earth's atmosphere is the gas that piles up on top of us, that we are immersed in and that we have to move through. So zooming out here, we've got our crab in a liquid fluid underneath this gaseous fluid, and here we are, crab beings scuttling about in a gaseous fluid above which is the vacuum of space. And just as we know, the water pressure increases as we go deeper into this tank, the air pressure increases as we go from outer space down towards the surface of the Earth, from a pressure of 0 at vacuum, low air pressure, and down here where we move about in high air pressure. So we want to be able to calculate how the pressure in a fluid changes with depth. So we need a model for handling fluid physics. This picture here shows a water balloon being tossed, and we've traced out the parabolic arc followed by the center of mass of that balloon. And I'm indicating like 3 different models for how we can simplify the complex physics of this motion. Model 3, the most simplified method, is the one we've used thus far, that of classical mechanics, where we just treat the entire water balloon and all the water in it as a single point mass. And we draw the FBD for this one point mass located at the center of mass of the whole balloon. That's the greatest simplification. Over here, model 1, the perspective of statistical mechanics and thermodynamics is the most complex. That's where we take seriously the motion of all the zillions of individual H2O molecules bouncing around inside that balloon. But there's a middle way. Model 2 is that of fluid mechanics, or also known as finite element analysis. That's where we take the fluid motion inside the balloon seriously, but we break up the liquid into a bunch of little cubes called fluid elements. It's like sort of a Minecraft view of the universe. If in Minecraft the air was made of blocks and the water was made of blocks too. So here we've got this sort of grid of little blocks of water that can bend and warp as the water's in motion. Those are our fluid elements. I colored in a few of them in pink here. So that'll be our subject of study. This picture here shows a section of the surface of the Earth, and we've got distance marked out in meters, and so our scale is that 1 unit is 1 meter here. And then vertically I've got a scale also in meters, so 1, 2, 3 meters off the ground. And we're going to imagine this Minecraft sort of world in which the air itself is a stack of cubes. So I've colored one in pink here. This is a cube-shaped fluid element. So that is a cube of air. We know that the air pressure should increase somewhat as we head deeper and deeper into this aquarium full of air down toward the surface of the Earth, just as water pressure increases as you go towards the bottom of a pool. And I've highlighted here in yellow one particular column of air. A column of air that is, let's say, that has a square cross-section with a 1 meter by 1 meter square base to it and extending all the way up to outer space. Let's look at the free body diagram for this 1 meter by 1 meter column of air. All right, well, the air is made of atoms and they have mass, so there's a center of mass to this tall column of air. That center of mass is going to be very high off the ground, so it's not where I'm showing it here in this picture. It'll be much higher up, but there's a center of mass somewhere, and so there will be a total force of gravity pulling on all of these air molecules. And then at the bottom, there will be the normal force from the ground pushing upwards on this tall column of air, holding it up. And so if our column of air is at rest in static equilibrium, then the net force should be zero. So the normal force pushing up on the column must be equal to the weight of all the air in that column. And then according to Newton's third law, if the ground pushes up on the air with this size force, then the air is pushing down on the ground with an equal sized force, which we see is also then equal to, in size, the weight of that column. So the force exerted by the air column on the ground according to N3L. And this allows us to define the pressure that this column of air is exerting on the ground. The global mean air pressure at sea level, that is a height z of 0, is found by taking the weight of such a column of air divided by the cross-sectional area of the patch of ground on which it rests. So if we've selected a 1 square meter patch of air here, then we would compute that the pressure is equal to 101,325 newtons per square meter on average. This is the global mean air pressure at sea level, 101,325 newtons per square meter. We have a special name for this amount of pressure. It is defined to be 1 atmosphere, ATM for short. In blue is our SI unit, newtons per square meter. That's what we have to use in our calculations. But it'll be convenient to refer to pressures in terms of atmospheres. So the air in the room that you're in right now has a pressure that's pretty close to 1 atmosphere. That's the air pressure that we live in most all of the time. So if we take this equation and say multiply that pressure times the cross-sectional area of the base of that column, then we would get the weight of that column of air. So the force of gravity, or the weight on that column, equals that pressure times 1 square meter. So 101,325 newtons per square meter times 1 square meter would give us 101,325 newtons, or approximately 10 to the 5th. This is about 100,000, so 10 to the 5th newtons. That is the weight of a 1 meter by 1 meter column of air that extends all the way up to space, 10 to the 5th newtons. Let's consider some implications of that. A couple of examples here. That means that on top of your head right now is a column of air extending all the way up to space that you're holding up. The air sitting on your head like a basket that you're balancing. Let's see, if the surface area of the top of your head is about 100 square centimeters, and quick unit conversion here, if there's 100 centimeters in a meter, and we square this, that means there are 10 to the 4th square centimeters in 1 square meter. So we'll use that conversion down below. Then the force of air pressing down on the top of your head right now is given by the air pressure in the room, which is about 10 to the 5th newtons per square meter, times the cross-sectional area of the top of your head. So if that's about 100 square centimeters, then that is about 100 times 10 to the minus 4 square meters. Cancel out our meters squared right now, right there. And that shows that there are about 1,000 newtons pressing down on your head. That's the weight of the air extending up to space that you are holding up right now. You are like a pillar holding up this basket of air. 1,000 newtons, that's about the weight of 100 kilograms or 220 pounds. 220 pounds of air sitting on the top of your skull right now and pretty much all the time. And because it's always there, we don't tend to notice it. So you might ask, well, should that force appear on a free body diagram for me? Should I be showing 220 pounds or 1,000 newtons of force pressing down on the top of my head all the time? Well, let's remember that that air is pressing down not just on the top of your head, but that air is going to be underneath your armpits and underneath your butt and underneath the soles of your feet a little bit, if there's not a perfect seal between your shoes and the ground. That air is pushing down not just on the top of you, but it's also pushing up from all those underside parts of you as well. So this downwards force of air on you is balanced out by upwards forces of air on other underside parts of your body, canceling out for the most part, so we don't need to worry about it on a free body diagram. But it does still press on your body as a whole, and your anatomy is accustomed to that pressure. This 10 to the 5th newtons per square meter of pressure on not just the top of your head, but on the side of your face and on your elbow and on your chest, and pressing in on all parts of your body all the time. That's a fact of life. Second example here is the idea of a suction cup. Suppose we've got like a little plastic suction cup here pressed onto a flat surface. And the idea with the suction cup is that you do create a tight seal such that there is no air able to get in around underneath the plastic cup. So we can actually create a bit of vacuum or near vacuum in that space right there. And in that case, the air pressure above pushing in on the suction cup creates a large force like this 220-pound force on the top of your head. But with this tight seal, there's no air underneath pushing upwards on the cup to cancel that out. So suppose we have a suction cup, just to put some numbers to it, that has a mass of 1 gram, and it's about a 4 square centimeter area. Then let's see, with a mass of 1 gram, then the cup would have a weight of about 1/100th of a newton. That'd be the weight of the cup there. So to lift up this suction cup, if it wasn't pressed tight, you'd only have to exert 0.01 newtons of force to lift up this 1 gram cup. But let's look at the air pressure pushing down on it. That'll be given by the air pressure in the room, about 10 to the 5th newtons per square meter, times your cross-sectional area, 4 square centimeters, or 4 times 10 to the minus 4 square meters. Meters squared cancels meters squared. And we would get 40 newtons of air pressure pushing down on it. Compare that 40 newtons to the 100th of a newton, that's the actual weight of the thing. So when you're trying to pick up this suction cup, if it's stuck on there tight and it's hard to get it off, what you're pulling against is the entire weight of the Earth's atmosphere pushing down against you.